Hey folks, welcome to the conference. I hope you're enjoying yourself. Uh, my name's Andy Banta. I'm here representing Magnition, and I'm here to talk to you about optimizing complex hierarchical memory systems through simulations. This applies to storage systems as well. Uh, uh, you can find me at Andy Banta on Twitter. I also have a blog, andybanta.substack.com. You can see I bounced around the storage industry, high-tech industry for quite a while, doing a variety of different jobs. At this point, I'm just a storage janitor. So let me talk a little bit about the problem that we're going to address today. The idea is that compute systems and storage systems these days have numerous tiers of both memory and storage devices in them. These range all the way from very high speed caches for the CPUs, all the way down to like tape and archivable devices. And being able to figure out the right sizes and the right way to tier these, the proper components to piece together, the proper interconnects to piece together is very complex. And the number of layers keeps increasing, making the problem even more complex. This is where Magnition comes in. Magnition is working on ways of figuring out where to place data, how to size things, what interconnects to use. We're doing this mostly through simulations. We also can do it real time in a runtime environment. We're proven we actually have done this. It's being used in a storage system that's being delivered by a company that's represented at this conference here today. And we do an awful lot of research papers and patent applications as well on the technology that we've been doing. And we've actually previously won awards at the shows in the past. So let's get into how Magnition actually builds simulators and does simulations a little bit. We do this by having a handful of building blocks that you can use and allowing you to piece them together to build the simulator that you want. The components can be pieced together in a variety of different ways just by the ways that you interconnect them. You don't end up with a set model. You can try all sorts of things. And then we allow you to run a handful of simulations against it and then try, have a very small set of variables that you use to play around with and try out various different things. We recommend using simulators because first off, they're easier to build to actually try to build genuine systems, having to get all the components necessary and piecing them all together and allowing you to try things. It also allows you to try out different algorithms, try out different pieces and parts that you want to fit together. Hardware vendors, ASIC vendors, actually run lots of simulations on hardware chips and boards before they even go into production with them. The same isn't true about software. The software seems to be a hit or miss proposition, and there's no reason why software shouldn't be run through simulators just like hardware is. It gives you the benefits of this are decreased cost, increased speed, and way more flexibility than you would have just trying to build genuine systems or trying to guess what would be the appropriate way to do things. The components that we have are a variety of different things. We use a framework from people up the road here in Berkeley named Lingua Franca. They build simulators and they have the components of them are called reactors. So we use each one of these reactors to simulate a portion of a compute or storage system. Magnition's goal is to have a library of these reactors that are available for general use and allow you to build your own as necessary. We typically take open source projects and convert them into reactors simply by putting them in the appropriate framework. the basic building blocks that we consider when we actually are building these simulations are a cache. And for those who aren't familiar, we are typically dealing with hit or miss caches. So the idea is that you have an input of some sort that gets converted into some sort of key by way of the cache, and then the cache will look up in that by that key and see if it actually has the information you want cached inside of it, or it has to go off and get it from a different source. So if it's a hit, it will look at it will return the information quickly, and if it's a miss, it will have to pass the request along. And in both of these cases, what it's hitting or missing would be a media of some sort. So memory, disk, tape, cloud, any one of these would be considered media sources. And we use the media sources simply as a source of latency, not necessarily a source of data. When we're running these simulations, we don't actually expect to be returning real data. We simply would say it would take this long to actually return data. And then the final component that we build into these are considered wire components. So these also are just simply sources of latency. These would be things like the internet, or a memory bus, or a disk converter, or a disk controller. These are various different types of things. The exact types of things that we would be talking about as storage developers at this conference. And since it's composable, we can actually make multi-layer caches where we can build as many layers as we want and just keep building the components together to represent the system that we want to simulate. So let's talk a little bit about what our media components would be. This would be like memory or disk, or potentially cloud. One of the simulators that we actually have is called MQSim, which simulates SSD. It simulates contention and queuing and the latency that would be necessary to get data off of an SSD. The same would be true of like a RAM simulator or a disk array simulator. And again, I mentioned that we only need to simulate the delay. We don't actually have to have a storage device that has all the information that you would want in your system. Where all we're trying to do is figure out the best way to get rid of latency in your system. So in this case, like our first source could be DRAM, and our first level cache could be DRAM, and our second level cache could be an SSD. And finally, if we don't hit in either one of these caches, it would come from a storage array somewhere, like iSCSI storage array. Then we have the wire components, and the wire components would be a web server, or some other source that would be coming in. If it was like a content delivery system, we would be taking web requests. If we were modeling more like a multi-level CXL system, it would be a memory request. It would simply be we need this block of memory. In this case, our first level cache would potentially have like a RAM bus connection to our DRAM, or since we're here at the Storage Developer Conference and there's lots of talk about CXL, we could just say that's a CXL connection. In between the various different levels of cache, we would probably have something like a PCI bus. So in between the first and second level cache, there would just be a PCI bus connection, and between the second level cache and an SSD, probably something like NVMe. And then finally, if we don't hit it in the second level cache, we would have an iSCSI connection out to our final source, our final destination. So just like there were various different components in the simulation, the caches themselves actually have a handful of different components as well. A cache would be, we actually break caches down into lookups, allocators, lookups, and eviction algorithms. And we work with the idea that a cache can have multiple hit or miss rates, hit or miss paths. The example that we're using today simply has one, and you just can keep building on these as many different components as you want. There's a huge number of variables. We talk about things like cache allocators. These are just like another building block, like the media or the wire components that we had elsewhere. Things that go into a cache allocation schemes are like, is it a variable or a fixed size cache? It's something like you're caching a disk system, which would be a fixed size cache, or you caching like web pages or objects, it would be variable size. So that makes a difference. If you're using a memory cache, you would potentially have a variety of different memory caches or memory cache allocation methods that you could use. Or, if you're caching to an SSD, there's all sorts of other issues that you run into. Typically SSDs, you have to write them at about 1 megabyte block, so you would potentially need a fill buffer to fill up before you actually wrote it to the SSD as well. Similarly, there's a handful of different things that you could use for lookup algorithms. The hash algorithm, or the way that you actually do the lookup itself, is one component, but that's not nearly as interesting as some of the other components of the lookup algorithm, which would be what happens when you have a miss. Does that mean that, like on a disk cache, you would go off and do predictive allocation? Like lots of times disk caches will say, if you are reading one block, there's a good chance you're going to be reading subsequent blocks very soon, and they will go try to fill up the cache and take care of that. The cache allocation will potentially trigger an eviction somewhere, and you need to know what's going to happen on a miss, and I'm sorry, will trigger an allocation and possibly an eviction. And one of the other tricky things with the lookup is, if you have a miss, what happens if there was a very similar miss recently? You don't want to have to go fetch the same data twice. You actually want to wait for that first miss to finish and then just use the cache data. Other important part of the lookup algorithm is actually aging the contents of your cache. So when you look up something, you might want to say, hey, this was looked up fairly recently, and that way you know that it's warm data instead of cold data that you potentially want to evict from your cache. Another thing that you need to think about with the lookup algorithm is what happens if the underlying data is no longer valid. What happens if you have a valid key, but the underlying data has changed? You want to be able to say, we need to go fetch the data again rather than get it from the cache that we have. And similarly, evictions, there are a handful of different methods that you can use. What to evict from the cache. It's what happens when you have invalidations, like I was talking about with the lookup algorithms. And SSDs get particularly interesting for evictions, because again, lots of times if you're writing to them in 1 meg blocks, you need to evict from them in 1 meg blocks as well. And what happens if some of the data is out of date but not all of it? How do you handle that situation? So what I've described, it provides a variety of different components inside a cache itself, as well as a variety of different components that all fit together. When we get into something like this multi-level cache that I talked about earlier, there's hundreds of different variables that could be used here for various different compute or storage systems. You could have different interconnects, you could have different cache algorithms, you could have all sorts of different media, and you would potentially run into the case of whether this is a single cache instance or whether there are multiple cache instances. This is actually one of the experiments that we have an intern working on right now, and one of the things that I'll talk through with you. Our intern is working on algorithms for optimizing a content delivery network, taking requests to come in and running them against a multi-level cache. which is very similar to what we had shown earlier with DRAM and SSD being the two layers of cache, and then cloud being the final origin media. The work that she's been doing has largely just been dealing with cache algorithms rather than the wire and media components. And specifically, what I'm going to talk about today are the eviction algorithms. She's been trying different eviction algorithms with a various different number of points of presence or POPs within a content delivery network, and trying to optimize which eviction algorithm works when you increase the number of POPs. So let's get into how we do this. Magnition has a viewer that allows you to take a look at the various different components that are available. Let me get this playing. There we go. So it's, you started from a command line like most developers do, and you come into what we call the Magnition Designer, and you can go in and choose your project. And once you choose your project, you can go in and choose the source file. This is just pulling it from GitHub. And here we're going to pull up our content delivery network simulator. And here you can see the code. This is the starting code for the content delivery network. And on the right side of the screen, you can see that we actually have a visual representation of the code. So what you see on the left side of the screen actually is represented in the diagram. You can see the components and the various different ways that the components are interconnected. So if we blow that up a little bit, you can see that we have a load balancer which allocates different requests to a POP tier. So the POP tier would be points of presence, a series of points of presence. If we drill down into the POP tier, we can see that it has a pair of load balancers that basically send requests to a POP and then send miss requests out of the POP off to our origin media. And if we drill down into the POP, we can actually see that inside each one of these, this would represent a server. And inside each one of these, we have a pair of caches and some load balancers and various different pieces. All the lines represent the interconnections between them, the data that actually gets passed between the various different components inside the server. If we zoom in a little bit, you can see there's the L1 cache and the L2 cache, one on top of the other. And if we drill down into one of the caches, you can see that we actually have the components I mentioned when I was talking about caches. We have the allocation algorithm, we have the lookup algorithm, we have the eviction algorithm, and we have a controller that controls the interaction between all of these components. And this actually allows us to get the visual representation of what we want, and you can see all the various different components and all of the various different pieces of data that move around this UI. Our goal is that at some point we actually hope to be able to have the UI generate. The UI is generated from code right now. Our hope is that sometime in the future we will be able to have the code generated from the UI. So you will be able to move building blocks into your UI and have the code generated from it. As I mentioned, each chunk of the code, each chunk that you saw in that diagram represents a reactor or a simulator for a particular component in our simulation system. Once we have the simulation put together, we actually run it against real data rather than actually doing simulated or artificial data. We don't do things like running iometer against them. We actually use genuine traces to run against our system. Right? This is just an S trace that I've shown here. In actuality, we would have like an HTTP log full of the various different HTTP requests that would come into a content delivery network. these can potentially come from multiple sources. The ones that we're using are actual traces that were given to us by a handful of different content delivery networks with the data scrubbed to be anonymized, so we can try various different genuine workloads these content delivery networks are working with. And that's important because not all content delivery networks are going to be delivering the same type of thing. Something like a Wikipedia is not going to be delivering the same types of things as a YouTube. They're going to be providing entirely different hit rates and things that would be interesting and important. So once we actually have the simulators put together, we can actually, this would be like a map of 100 different runs with using a variety of different count of L1 and L2 caches in the entire layout. So here you can see that as we increase numbers, our hit ratios our miss ratios go down a little bit. Simply this is, this provides us some interesting data. What becomes very interesting is when we can actually compare different sets of data. So in this case, rather than just hit or miss ratios, we're actually showing the latency in microseconds that are generated when we have a variety of number of L1 caches and L2 caches. And in this case, you can actually see that our latency goes up as we increase the number of caches. And if you think about the way a cache works, this kind of makes sense in that if you have a single source of reference for all of your cached information, there's much better chance that you'll get a hit on it. If you have multiple sources of information, a request that went into one might be cached on a different server, and you'd get a miss. So by comparison, all we did was change the eviction algorithms based in the caches, and you can see in this case we've actually kind of flipped the map back over where the latency becomes better when we increase the number of caches. So this would be something that would be valuable for a content delivery network to know that if you have a certain, if you use certain eviction algorithms and you have multiple points of presence, you're actually going to be hurting your latency rather than helping it. So if you just change your algorithms a little bit, you can end up with better hit ratios. This is the type of value that Magnition can offer by allowing you to run these things through a simulator. So let's try to put a bow on this entire thing. As I mentioned earlier, Magnition has worked with a big vendor, a major vendor that's here at the conference. And before they started working with us, their performance engineering team was able to run about 2 experiments a day. By comparison, after they started working with us, they were able to run thousands of experiments a day. Over the course of the project, before they started working with us, they'd run about 50 experiments on the various different ways that they were doing caching. And after we were done with the project, they'd run millions of simulations and actually saw double-digit improvements in their cache performance before shipping the product. At the end of the day, hopefully you can walk away with the idea that simulators allow you to actually build complex systems in modular ways very simply and quickly. This allows you to attack real-world problems more inexpensively, more quickly, and more flexibly using simulators. And the end results are that you end up with better results for your customers and less time and resources spent on your own. Thanks very much for listening to me today and attending. Please do fill out the survey. STEAM appreciates it. I appreciate it. Everybody here associated with Magnition and the conference appreciate your feedback as well. I certainly take it to heart when I get it. Thanks again.